Hello. Hi, everyone. Let's get started with our Unit 2 material for today. So for today, hopefully you've printed out this Unit 2 brackets, and we're only going to go up to 2.1. We're going to talk about 2.1, 2.2, and then 2.3. So if you can't print out this packet, or if you're taking paper notes, just be prepared to take about 6 pages, the first 6 pages of this. All right. Now, I'm going to warn you before you start the video. This is going to be very mentally intensive. So you're going to have to pay attention to a lot of the things I am saying while also having a mental image of what I'm trying to describe. Um, and I'm kind of foreshadowing the difficulty of 2.2 because here we have to use some arbitrary thought that isn't it's a bit of like you have to make the mental image yourself. But maybe I'm getting ahead of myself. Let's start off with just 2.1. So 2.1 talks about the area between two curves. Definite integrals represent the area between the graph of f of x and the x-axis from some a to b. Theorem states if f is a continuous on that interval, then f is integrable on that interval. So find the area under f of x equaling negative x from x is 0 to 2. So that's just a fancy way of saying define the integral. Okay, so that's the integral from 0 to 2 of negative x. Okay, dx. Well, we know that first I can take out the negative, and then we know that this is just a power rule, so negative x squared over 2 in parentheses, and then from 2 to 0. So then from here, we plug in 2 and we plug in 0, and we have 4 over 2 minus 0. So that's just 2, and then we just have a negative 2 as our full answer. Now keep in mind that the gimmick here was that it does it from the x-axis. So for example, just mentally, if I drew, the negative x line, I would have it here. And we could see that the area between that and the x-axis is in the negative space. So that's why we see negative 2 as the area. Now, this idea is a bit cumbersome, and it's also not encapturing the full picture of finding an area. So that's where the idea of an area between two curves is going to be introduced. To find the area between two curves, f of x and g of x, where one function is greater than the other, f being the top part and g being the bottom part on a and b, then the area is defined here, where it's that integral, or where it's that um, interval, and f is the top and g is the bottom. So visually here, we can see that f is on top of g. Now, in some cases, we provide the interval, and in some cases, we don't. This is one of the cases where we don't. It says find the area between y is equal to x and y is equal to x squared. We are not given an interval. We need to make one. Find where the functions intersect, because in reality, they're going to intersect. If we're going to find between, it can't just be an infinite in between. There has to be some overlap of these guys. So let's go ahead and figure that out. The way we can figure out at what points they equal is setting them to equal. So we have x is equal to x squared, and we're going to ask ourselves, okay, what value do these guys equal? Well, first, there's the trivial value of doing this to be well, never mind. I was gonna say there's a trivial value, but let's actually just do something really simple and make it to where all the x's are on one side. So I'm gonna subtract x. And then from here, I get factor on x, and I get x minus 1. Then I could split these up using the zero product property. We get x is equal to 0, and x minus 1 is equal to 0, which means that x is equal to 1. So it's both the case when x is 0 and x is 1 that they'll have that intersection. So we know that at 0 and 1, these functions should have the same value. Let's double check that. When x is 0, y is 0. When x is 0, x squared is 0, y is 0. And similar things for 1. But we don't know at this moment what the top and bottom function is. Because remember, the top and bottom is going to matter a lot. It's going to determine if we do this interval from 0 to 1 of x minus x squared, or we do this interval from 0 to 1 with x squared minus x. So let's pick a number in the middle of these guys. I'm going to pick a simple number. I'm going to pick 1/2. When x is 1/2, y is 1/2. And then when x is 1/2, y is 1/4. So clearly this is bigger. So that means this will be on the top. And this will be on the bottom. So x is on the top. That means we're going to use this guy. All right, well, let's go ahead and solve this. Well, we know that we can just distribute that that integral, excuse me, from x dx 0 to 1 minus the integral from 0 to 1 x squared dx. So we know if I plug these in, we'll get x squared over 2, 1 0 minus, and then x to the 3 over 3, 1 0. Plugging that one in first, we get 1 over 2 minus 0, and then minus 1 over 3 minus 0. Getting rid of the minus zeros and simplifying the negative, we have 1 over 2 minus 1 over 3. That's a butterfly property problem, or butterfly addition subtraction problem. So 1 times 3 minus 1 times 2 over 2 times 3 becomes 1 over 6. And that's going to be the area in between x and x squared. Typically, we can use the phrase units to define the area, but I'm not too stickler on these. They aren't relevant just yet. It's only when we're doing applications problems that they're really relevant. All right, let's practice another one. So this time, it says find the area between y is equal to x plus 2 and y is equal to x squared from -1 to 2. Now this is I want to practice something just right here first. I want to practice that we find that these are the intersecting points, and I also want to verify that these are the only intersecting points, because technically there does exist a function, and we will do that in we're definitely gonna do that. Hold on, give me a second. I realized I forgot to turn on the slides, which I don't know how much it'll help. Wait. Yeah. Um, that what was I saying? That for we want to practice intersecting points because technically there exists a function where let me color code. Where you have one function that's basically like this, and then one function that's basically like that. So it can like switch between the top and the bottom, what's in the top, what's in the bottom, especially if you're asked like for the interval between here and here, right? So just keeping that in mind. So let's practice that still, just in case. We want to find out when they intersect to where they're equal. So x squared is equal to x plus 2. Make everything go to one side. So we can make it equal 0. For here, we have to factor. I'm going to use this method. I think I did too many lines. Give me a second. Oh, look at this whiteout I found on Amazon. It's so cool. It's in the shape of like a. Oh, I just dropped the cap. But it's in the shape of a milk ball. It's so cool. Okay. Anyway, not the point. What did Professor do during class? He just talked about his new whiteout. And what of it? And what if I just talk about my new whiteout? I'm just kidding, obviously. Give me a second. Okay. Right. Anyway, let's see. So let's just fill in some blanks. So I have -2 here, and we could talk about what numbers add up to -2, or we could figure out one. Then we have x squared here. So we know that these will very least be an x and an x. But we need to ask ourselves, okay, um, what product of -2 adds to -1? Well, that's probably just going to be 2, no, -2 and 1, because if I do -2x and then plus x, that'll be -x. Okay. So my answer is x plus 1, x minus 2 is equal to 0, 0 product property ensues, and we get x is equal to -1 for one, and we get x is equal to 2 for the other. Okay. All right. Let's see. From here, we definitely are just using those endpoints, so there's really nothing to check, which I kind of gave away with my notation, but it's still important that we double check. All right. So it's almost like the last problem where you start off with a -1 and 2, and we see that it's going to be y is equal to 1, and over here y is equal to 1, and over here y is equal to 4 and y is equal to 4. So it does intersect, but we need to double check at what point do we know what's the top and what's the bottom. So we're going to use 0. When y is 0, we have when x is 0, y is 2, and when x is 0, y is 0. So this is definitely the bottom, this is definitely the top. So our integral from the bounds -1 to 2, since they're specified here this time, say that we are supposed to do x plus 2 first minus x squared dx. From here, I'm just going to separate all of the variables. We have the integral of x dx plus the integral of, we'll take out the 2 dx, and then minus the integral of x squared dx. This first part produces x squared over 2 from 2 to -1. This second part produces just an x. And this last part produces an x to the power of 3 over 3 to the -1. So, let me color code just a little bit for these. See. So for this one, we have 2 squared divided by 2, which is just going to be 2 itself because it's 4 divided by 2. So 2. And then minus 1 over 2. Because there's no double negative, because -1 would be 1, but we're still subtracting. And then for this one, it's just going to be plus 2 of 2 minus a -1. And then for this one, we have a minus and then 2 to the power of 3, which is 8 over 3. Negative 1 to the power of to the power of 3 is still negative 1. So we'll have a minus a negative 1 over 3. Hold on, I'm realizing that maybe to me they're different because this is purple and this is uh actually this is kind of a shade of purple as well. Dang it. Okay. Let me let me just redo that real quick. I apologize. Okay. Some of you are watching, you're like, I bet he just wanted to use this whiteout. I'm like, maybe. Maybe subconsciously. Okay. Minus on the front, we got 8 over 3, and then minus a negative 1 over 3. Alright, this part simplifies to 3 over 2. This part over here simplifies to 6. And then this part over here, that becomes 9 over 3, which is just 3, so minus 3. Right? Then from here, we're gonna do, I guess I'll do the right hand side first. 3 and then 3 over 2 plus. So, I'm being lazy, but I'll just do it out loud. We got butterfly method, that's 3 plus 6 over 2, which is 9 over 2, which is my answer. Okay, give me a second. I'm just making sure I'm not forgetting anything, because what I do before is I have like basically a cheat sheet. Here, I'll quickly show on screen. Oop, there it is, secret. And I just want to make sure that I don't miss any steps. No, we're good. Okay. Okay, and that's the answer. All right, now I'm introducing a new level of difficulty that isn't too difficult, but it's the thing where like the notation has the potential, like just in general, has the potential to trip us. So now it's the area between two curves, but horizontal slices. Vertical slices mean you slice along the x-axis, so you're doing this sort of measurement by the x-axis with the two curves. But sometimes it's easier to slice horizontally, especially when the functions are given in x equals instead of y equals. So you rewrite the prompt to just be on its side, where we're using y as the input variable and x as the output variable. Let f of y and g of y be continuous functions such that f of y is greater than g of y. F of y is on the right, and g of y is on the left. That'd be the pseudo top and bottom. Then the area is defined here. Find the area between x is equal to y squared and x is equal to negative y plus 3. So here, similar vibe. We're not given a point where these intersect. So we need to see when they intersect. How do we see? When they eventually cross, when they have the same value. So y squared is equal to negative 2y plus 3. Throw everything to one side. And then we need to factor this. We need to ask ourselves what products of negative 3 add up to 2. I'm going to go ahead and let me go ahead and write it out just in case. I may be overthinking it. Okay, we have y squared, which just will be y and y. And then, oh, I was definitely overthinking it because then this is 3 and this is -1. And that will be our y times 3, 3y, y times -1, and that'll be plus 2. Okay. Ah, I forgot. Negative y. Alright, so then we have y plus 3 parentheses, y minus 1 parentheses is equal to 0. And then we have y minus 1 is equal to 0, which implies y is 1. And then we have y plus 3 is equal to 0, which implies y is -3. So we know that's going to start at -3, and it's going to start at 1, or going to end at 1. So that means we need to figure out what x is at these 2 points. Well, let's start. In this case, x will be 9. And in this case, we have 6 plus 3. X is 9 as well. Then when y is 1, x will be 1. And when y is 1, x will be -2 plus 3, which is 1. So now we need to pick a number in between these. I'm just going to pick an easy number, 0. So when y is 0, x is 0. And then when y is 0, x is 3. So this guy will be above this guy. So therefore, the strategy is we write this guy on the top. Now, granted, you're using right and left, but top and bottom language can apply here as well. So let's go ahead and do that. We got -3, 1 of -2y plus 3 minus y squared dx, or dy, excuse me. Now, just remember you're treating y as the input variable, so we just have to pay attention to the notation, which can get confusing, especially when you come off of a topic like implicit differentiation, but I promise this is a better way to do it. Before, I remember doing these, and our professor just told us, like, rewrite everything with x, but I've never liked that because that just is confusing. So I think this is the best way. But if you want to, you basically can write a bizarro version of this where you rewrite everything with x, y, and you write everything with y, x, given that you know that this is the type of problem you're dealing with. Okay. Where was we need to do that integral -2y plus 3 integral -3 1 dx or dy, sorry, dy, and then minus integral -3 1 y squared dy. -2, we have y squared over 2, 1 to -3. And then over here we have 3 of y, 1 to -3. And over here we have y to the power of 3 over 3. And then this, I'm just going to quickly simplify, take out the constant here, just so that I don't have to worry about it. Let's see. In fact, maybe I should have taken out the constant over here too, so we don't have to deal with that fraction nonsense. Actually, I will. I'll do that, but I'm gonna do it in the same step. So let's start here. I have a negative, and then we do 1 squared, which is 1, -3 squared, which is minus -3 squared, which is 9. Then, following this step, I have plus 3 times 1 minus a -3. And then with this step, I'll write -1 over 3 with 1, and then minus, because the negative will stick out, and a negative 27. Okay. This first part gets simplified to 8. This part, it's going to be a 4. That gets simplified to 12. And then this part over here, apparently that 1/3 didn't help at all. It gives us 28 over 3. Wait, let me just double check. Maybe I missed something. Hold on, let me see. Uh, no. I don't think I did. Okay. So let's go ahead and do this. We have, I'm going to simplify the first part of 20 minus 28 over 3. And then we rewrite that as 20 times 3 minus 28 times 1, which doesn't matter, over 3. We have 60 minus 28 over 3. That's going to be 32 over 3. And that's going to be the answer. All right, that's pretty much it. I think the only thing I did in the other step is that I didn't simplify this. I went ahead and did, or I didn't take out the 1 over 3, so that's why it threw me off for a moment. But unfortunately, you still have to deal with the fraction. Sorry. All right, one more time. We have find the area between x is equal to y squared and x is equal to 9 from y is -1 to y is 2. Okay, so from here, we have to ask ourselves, okay, well, when do these guys intersect? Now, granted, for this problem, we're paying attention to how, here, let me show you. These are both using x as the output variable. So this is still going to be of that y format. So from here, we can do y squared is equal to 9. And then from here, you can do the 0 trick, or actually, let me quickly just move this to the side, just because we're probably going to need that space. Y squared is equal to 9. You can move it to one side, or you can just recall that for when you square root both sides, it becomes plus and minus the square root of 9, which we know the square root of 9 is 3. So now we have a technicality. The technicality being is that the points where these two functions would intersect are beyond this interval. So because they're beyond this interval, you don't really have to check if there's a middleman inside of it. So for example, it's saying that this function, regardless of how they're touching, which we know how they're touching, but just to be arbitrary, it's saying that over here and over here are the only points that they touch. This is at -3 and this is at 3 respectively. Um, oh wait, it's vertical. My mistake. Well, you could just, let's just do this then. It's 3 and -3. Ugh. But if we just zoom in, right, to what would be -1 and 2, they really don't intersect again. So you're still doing the same interval, but you don't have to worry about breaking it up further. You're just zooming in, really. And you still have the same technicality where you have to check if one's above or bottom. But you almost really don't even need this middle part anymore because from zooming in, you should be able to see what is on the top, or I'm sorry, what's on the right and on the left. So let's go ahead and just do this as it is. So when y is 2, x is 4. When y is 2, x is 9. When y is negative 1, x is 1. And when y is negative 1, x is, well, 9. And it doesn't seem like no matter what you pick here, this technically doesn't matter, 9 is greater than both of these guys. So that means this will be on the top. So that means your integral should be set up from negative 1 to 2, because you're being told to zoom in basically, of the topmost, which is 9, and then the bottom, y squared, dx. I mean dy, sorry. Wait, did I write dy for the other one? Okay, good. Now we need to make sure that we're following those steps. Okay. So for here, distribute out, we get integral of 9 dy minus integral negative 1 9 y squared dy. Over here, it's going to be y. Wait, why write 9 here? Okay. 2 negative 1, and then over here, y to the power of 3 over 3 of 2 and negative 1. Okay. I'll color code this as well, just to play my cards. Save. We have 9 parentheses 2 minus a negative 1. And then over here, we have 2, which is 8 over 3. And then minus negative 1 to the power of 3 would be negative 1 over 3. Okay, here we could have factored out the 1/3, but I guess you never really can for sure tell when to do a trick and when not to. Other than, I mean, not do a trick, because that's wrong, but when to do like a simplification of taking out the constant. Over here we have 9 times 3, which is 27. And over here we're going to have 3 over 9, which is 3, so minus 3. And that's going to be 24. All right, that's the answer. Let's see. Okay, that's pretty much it. Make sure that if this still left you unsure, that you look at the group work video, because we'll get a little more into it later, and then the homeworks are definitely going to get into it. So please keep that in mind. All right. Now for the foreshadowed harder one. Okay. Um, so sometimes we have arbitrary objects, right? And arbitrary objects can have these weird curvatures. But the curvatures can be defined theoretically by a function, right? There was some method to the madness. So we have two shapes of these functions with curvatures. It's the disk and it's the washer. A disk, you treat it as something that is um, circular, that is in a consistent circle notation. So you see here that we have almost this little like pinwheel, not pinwheel, the little thing that you wrap thread around if you're sewing. And we see that this is rotated to give us a circular shape. And even though like the radius decreases here and increases here, it's still a consistent circle. The washer follows a similar idea, but we call it a washer because there is a hole in the middle. So there's a hole from here to here. And this line is what you're determining the area as. So you're doing the disk, and the disk is defined as pi times the radius function squared from whatever interval you're slicing. And then the washer is two disks being taken out of each other, where you're finding the function of the innermost radius and the outermost radius, or outermost radius, innermost radius, squared, same thing, but they're subtracting, all with the coefficient of pi being added. So, find the volume of the solid formed by rotating the square root of x around the x-axis on 0 to 4. So that means that if we're doing the square root function that looks like this, we know that if it were to rotate, it would rotate, around. Here, let me do the radius as this, where this would theoretically be the radius. And we are trimming this shape from 0 to an arbitrary value 4. So this shape was to keep going in this tunnel format. It would be maybe right here, we could say that this is 4. Now keep in mind that it's rotating. So technically we can draw this line as well. This line is just it flipped, so if you wanted to know, which I kind of need you to know that visualization, while this line is square root of x, this line is the negative square root of x. Because it's just rotating, right? So think of it like that. It's here, I grabbed this cup. So think of it like this, where flat. This image here is just the function, and in reality, you're rotating it. So we see that it's not just a flat shape; it's a whole cone that we have to deal with, a whole disk that we have to deal with. So we have the integral from the slice we chose, 0 to 4, of pi times our radius, which we defined as f of x. F of x, square root of x squared dx. Well, before anything, a simplification I can make is canceling out the square roots and the square to get pi x dx. And this kind of becomes an easier problem in that way. Let's factor out the pi. And then let's go ahead and do pi of x squared over 2, 4 to 0. Or let me write out. 4 is going to be 16 over 2. And then 0 is just going to be 0. 16 over 2 is 8. So the answer is 8 pi. All right. Let's keep this going with another one. So find the volume of a solid formed by rotating this function around the x-axis on -1 to 3. So again, that means that we're taking this, which is let's see, it's going to be some U shape, so I'm not going to worry too much about what it looks like because I don't need to know what it looks like, but I'm practicing us visualizing it. Trying to think, would it be better if I gave you like the actual x-intercepts? I don't think you need it. I don't think at the moment, I don't think the x-intercepts are going to be much help. But either way, you would see that it's some U shape, and however high above the x-axis it is, well, it's going to go ahead and also be flipped here. And the radius is going to be from the x-axis to here, to here, to even here arbitrarily. And it's going to be forming this continuous disk notation. If you pick any point. Okay. But we're picking -3 or -1 to 3. So pi times this whole variable, x squared minus 4x plus 8 squared, and then dx from -1 to 3. Okay? From here, it's going to get a little ugly because technically we have to do this square process, which we can definitely do. I'm going to do it though on the side. Here, let me pick a different color for that. Okay. So I'll do it on the side here. We got x squared minus 4x plus 8 times x squared minus 4x plus 8. We have this guy over here, which is x to the power 4, negative 4x to the power of 3. Then we have plus 8x squared. Over here, we got negative 4x to the third plus 16x squared. And then minus 32x. Okay. Then we're going to do 8 times the x. 8x squared. 8 times the negative 4 minus 32x, and then 8 times 8, which is just 64. I'm going to combine like terms. We got x4, or here, this I do want to highlight because I feel like I'm going to get lost. X4 is the only one within 4 with the 3's. I have this one, and that's it. So minus 8x3. Then I have this guy, and this guy, which is just plus 32x squared. I have this guy and this guy, which is minus 64x and then plus 64. Okay. Let me just double check, because I don't want to worry about leading us astray for this. Mm, okay. Right. So then from here we can rewrite this. Where's my color? 3. I'll take the pi outside since it didn't affect anything. X to the power 4 minus 4x3 plus minus 8x3 plus 32. Let me see. Did I? Well, let me double check that I did my values right. So it's negative, positive, positive. Over here, negative, positive, negative, positive, negative, positive. Okay, all right. Let's keep it going because, okay, I'm gonna be honest, I have something else on my answer sheet, but I'm pretty sure I did it wrong. But we'll find out right now. Okay, x squared minus 64x plus 64. Okay, let's do the integral of these piece by piece. I'm actually gonna skip the step or where I split up the integrals and just write them out. So we have pi parentheses this guy first, which is x to the power 5 over 5. And then this guy, I'll take the 4 out. So it's just 2 x to the power of 4. For this one, this is 32. You can't take the 30. 32 doesn't have a factor of 3. So I'll just write it as x to the power of 3 over 3. That definitely has a factor of 2. So x squared. And then just plus 64 times x. All with the same bounds of 3 and negative 1. Okay. Now, for what I'm going to do here is I'm just going to write it all in a calculator just because I'm not going to bother having all of this writing out each and every step. So let me get. Okay, let me get this calculator out. We have 3 to the power of 5 divided by 5 minus 2 times 3 to the power of 4, and then plus 32 times 3 to the power of 3 divided by 3, and then minus, I'm sorry, yeah, no, minus 32 times 3 squared, and then plus 64 times 3. And this was all, um, let me do this. This is all at 3, so pi of 78.6. Then we're doing negative 1. So that one, I'm just going to kind of manually go what I've typed and just replace every 3 with the parentheses negative 1. I'm using parentheses because it's negative, so I wanted to make sure that the whole negative gets considered when I put in the power. Okay. Uh, and yeah, just negative 1. Um, we have a negative 108.867. Okay, for that, kind of disappointed. I didn't foresee this being and it's not, it's one of those things where this isn't a bad It's how do we say? This isn't a good example because we had to pull out a calculator. I could have left everything in exponential or like as a thing like this, but I just didn't want to. I don't know. Okay, it doesn't matter. The point is that we can still figure it out and we can still get an answer. It's just pi times this value plus 78.6. But I definitely wanted to give you guys something where the value was like a whole number. I think I just made that gap somewhere here, so just keep that in mind. That's your tests. Like for example, your test, my goal is like the hardest thing that you'll see notation wise is gonna be on your homeworks and lecture and group work. The hardest thing will not be the test. So you just have to keep that in mind. Which I know is not like the best thing to hear, but it's the honest thing to hear. Okay. Um, yeah, let me go ahead and keep this moving. Oh my God, this video is an hour. Oh, we gotta keep it going. There's no other way around this. Sorry, guys, it's gonna be an extra long video because we're on page 4. We need page 5 and page 6, and that's because we haven't even gotten. Oh, we're okay. We're just about to get into the washer method. Okay, so this says find the volume of the solid formed by rotating the region between y is equal to x and y is equal to x squared around the x-axis. So here we have an issue where we have this weird little sort of shape. And this is defined by one area, but inside is defined by another area. And we're secretly forming this sort of washer as we go about here. Now, granted, it says from 0 and it stops at 1. So visually, because they're using this image, that tells me that our integral is going to be from 0 to 1. But now we have a technicality. What is the outermost and what is the innermost? From here, you can do the table, but visually you can see that the outermost would be x. So pi parentheses x, remember it's squared, and then minus the innermost, which is x squared squared. And, oh, dx. In this case, we could take out the pi, and you have x squared, and then minus x to the power of 4. Definitely split these up. Or actually, I'll just do this as whole parentheses. Uh, pi, and then x to the power of 3 over 3, x to the power of 5 over 5, and you just have pi of 1 over 3 minus 1 over 5, which if you do product, butterfly method, you'll get 5 minus 3 over 15. So the answer is 2 pi over 15. Okay. All right, let's go ahead and move on to another washer. And this one says find the volume of the solid by rotating the region between y is equal to the square root of x and y is equal to x on the x-axis from 0 to 1. Okay. So over here, we have the square root, and then we have x. Now, let's pretend No, I think I accidentally made it easy by including this image. Or not easy. Easy is a strong word. I know. I I want to double check that we can tell what's the top and what's the bottom. So if you pick any point, let's say, point 0.5, right? We should be able to see what is the top and what is the bottom. So, or maybe don't pick point 0.5, maybe pick something that you can do the square root of. So let's pick 1 over 4, when x is 1 over 4. Y square root of x is going to be 1 over 2, and then x is going to be 1 over 4. So for sure, this guy is going to be below this guy. That's going to be on the top. Y 1/2 is greater than 1/4. So that means that our setup is pi, parentheses, this first top function, square root of x squared, minus the other function, x squared. And it says check from 0 to 1, so that's what we're doing. We can simplify that, and we could take out the pi. So we have x dx minus x squared dx. That's going to be x squared over 2 from 1 to 0, and that's going to be y3 over 3 from 1 to 0. Plug in 1s, plug in 0s. We'll conveniently get 1/2 minus 1/3. That's going to be pi over 6. All right. Let's see. Well, I'm not there on that page. Yes. Okay, sweet. All right. Now, from here, we are going to increase the difficulty 2 ways. Okay? First way is now we're back to the problem of flipping it on its side. So like the area problem before, where we flipped this on its side, doing horizontal, we are now flipping this on its side. And we're also going to go off center. And it's going to be our goal to recenter this. Let me explain. So find the volume of the solid formed by rotating the region around y is equal to square root of x, and y is equal to 0, and x is equal to 4, around the line x is equal to 5. So we're using this as our spinning point. So we're spinning this curve around here. Which in reality, if we're mirroring, means that it would look like this. And it would probably come, if it comes down in 4 steps, it's going to come down here in, see, let's do 4, in 4 steps as well. This line is going to be the square root of x. Y is equal to square root of x. So this line seems to be that flipped, and oh, this is also our x is equal to 4 line. But the problem is that it's on its side and it's off center. So one easy fix to make it centered is moving it. If we move everything to where this can be 0, then essentially we can make it center. Especially if we're only slicing it from y is equal to 0. So our whole shape is going to be from here to here. So let's go ahead and make it off center. We move everything by 5 units. So I know that I need to move this back. I move it 1, 2, 3, 4, 5 to make this 0. That's going to be -1, -2, -3, -4, -1, 2, 3, 4, and then that would be 5. That's going to be 5. So that makes this function a bit trickier to look at now. So let's do the innermost radius. So the inner radius, if we do this visual trick, is for sure going to be x. X is 1. Oh, okay, that's a good point. So because we're doing this, I even fell for this own trick question myself. Um, we should change this to be a variable of x, since we're doing it with the horizontal anyway. So this is going to be y squared is equal to x. Okay, so that means if we have this function y squared is equal to x, and we move it, that means we have to manually move this as well. So while the outermost radius is 1, and it circles around 1, what is this function? Well, the outer radius is, we know it's going to be of x, but we need to know that it makes that y curve. And it makes that y curve coming down. Let's go ahead and trying to think of what's the best way to describe this. Okay, before the shift, I should have done this. Before the shift, we know while this is y is equal to x, that it gets mirrored here. So it moves 2 and then gets flipped 2. But here we know that if it's that curvature, that it's that same movement, it just starts off. So we can move, here, let's talk about the transformation. So we can move x squared is equal to x. We can move this to the left 5. So y squared minus 5 is equal to x. And then we know it gets mirrored, so we flip. And how do you flip? You make what it's equal to negative. So negative y squared minus 5 is equal to x. That then can be easily distributed to be negative y squared plus 5. And the outermost radius is negative y squared plus 5. Okay. That was annoying. Sorry about that. I did tell this story out of order, so that's on me. I apologize. Okay. All right. Now that we have the innermost and outermost radius, we can still do this step. But remember, we're paying attention to the paying attention to the y slices. So from 0 to 2. And then the outermost, or wait, pi times the outermost squared, which is negative y squared plus 5, minus the innermost square, which is just 1, and then squared. Okay? This we can definitely just do. I'm gonna take out the pi. We get y to the power of 4, and then minus 10y squared, and then plus 25 minus 1, because 1 squared is 1, dy, and that becomes plus 24 dy. I'm going to practice us not separating these just to see if we can do it. So we have y over 3, or y to the power of 3 over 3, minus, oh wait, that's a 4. Oh, force a habit when I do a quadratic, so that's going to be 5 over 5. 10 of y to the power of 3 over 3 and then plus 24y. And remember, the way to check these is if you're doing the derivative, you should be able to get that back. So if we do derivative, the y disappears. If we do derivative, the 3 comes down, it's 2, that disappears. If we do the derivative here, 5 comes down, that disappears, so it's just the 4. Okay. Plug in 2, plug in 0. Spoiler, if all this has a 0, then it's going to be 0, so we really just need to plug in 2. Pi of 2 to the power of 5, which I believe is 32. Let me double check that. 32 over 5 minus, that's going to be 8, so 80 over 3, and plus 48. Okay. Let me see. Can I simplify any of these? That's not divisible by 5, so no. Okay. So let's go ahead and make this bigger. Unfortunately, I'm going to go ahead and put an arrow here. Let's see. 32 times 3, that's going to be 96. And then 80 times 5, that's going to be 400. Love that. Over 15. That gets simplified to negative, plus 48. That gets simplified to negative 304 over 15 plus 48. This, I'm going to go ahead and do negative 304. 15 times 48. I'm not going to do that in my head. I'm doing that in my calculator. 720 over 15. And then 1. Sorry. Wait, am I doing this wrong? Okay. All right. I'm doing that. 720 minus 304. 416 over 15. I'm just gonna double check. I don't think 416 is divisible by 3, and it's not divisible by 5 for sure. No, yeah, so that is the simplest form. Oh, pi. All of this I forgot pi, so pi, 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 pi. Right, and that's our answer. Okay, let's see. I know I put one of these on your homework. I don't remember. Let me check if I put one on your group work. Give me a second. Let me see. Let's see. I believe I did. Okay, good. It's number 3 and number 2 of our group work. So keep that in mind, okay? So we're gonna do this again, and I'm inclined to include one on the test. Although probably, if I do, I probably will make it kind of tame and maybe even give you a hint along the way of saying, like, remember, this isn't on the x-axis or y-axis, something like that. But no promises either way. All right, we're not done though. Even though it feels like we're done, we're not because we have this last page. On the bright side, this last page is the last page. All right, arc length. For curves, sometimes they have weird shapes. So, we can define arc length as the following. Let f of x be a smooth function. We want to calculate the length of the curve from this set of coordinates to this set of coordinates. Arc length is then equal to this expression. Calculate the arc length of the graph here over 0 to 1. Okay? Well, notice how in this one we use this full expression. So we should construct that expression before plugging into the here. So we start with f of x, and f of x is given to us x power 3 over 2. Let's do the derivative of this, which is just 2 times 3 over 2, x, and then minus 1, just be 1 over 2. That can be simplified to 3 square root of x. And then, from here, we want to square this derivative. So 3 square root of x squared. A square goes to the 3, and a square goes to that square root. That cancels out, and that becomes 9x as the whole expression. So what we plug into here for the arc length is 1 plus 9x dx. And you're finding it from 0 to 1. And remember the prompt of substitution. Wouldn't this be a lot easier if it was just square root of something? So let's just rewrite it. U is equal to 1 plus 9x. Du then must be equal to 9 dx. And because you don't have the 9 here, you can just make it to where it's equals dx. So you plug that into the integral from 0 to 1 over 9 of square root of u du. And then you have 1 over 9 u to the power of 3 over 2 over 3 over 2. I'm going to choose to just bring that fraction to the top. 1 over 9, 2 over 3, since it's dividing already, u 3 over 2. From here, I think I do want to simplify. So we have 2 over 27, u to the power of 3 over 2, and then plug in back u, 2 over, oh, I forgot to do this bracket. 1, 0, 1, 0, 1, 0. And then now, filling the whole thing plus 9x 1, 0. Okay. Oh wait, power 3 over 2. If I plug in 1, I get 10 to the power of 3 over 2. If I plug in 0, I get 1 to the power of 3 over 2, which we can just say is just 1. So maybe I don't even have to bother writing the 3 over 2. But it is a good step to follow. And then that would be the answer. Now, granted, you can't do a proper square root of, not square root, 10 to the power of 3 over 2 without getting some sort of factor along the way. So that's as much as we're going to leave it. All right. That typo I do remember doing. Or it's not a typo, it's just that it's not like a square rootable, or this doesn't have a whole number representation. I do remember doing it being like, well, it's not that crazy of a thing to get. All right, calculate the arc length of the graph, this, over 0 to 1. All right, similar vibe that I like to do is I like to figure out the whole expression. F of x is equal to 4 over 3, x to the power of 3 over 2. F prime then of x is equal to 4 over 3, 3 over 2, x to the power of 1/2, which technically is just 4 over 2, which is 2 square root of x. And then the whole thing squared is just 4x. So you plug it in, 1 plus 4x. You get u is equal to 1 plus 4x. Du is equal to 4 dx. You don't have a 4, so you gotta make it disappear and just reappear. 1 over 4, 0 to 1, square root of u du. 1 over 4, 3 over 2, u 3 over 2, from 1 to 0. Similar hijinks ensue from this point. You get 1 over 4, 2 over 3. This comes out to simplify as 1 over 6. And then you plug in back what you got for u, plus 4x, 3 over 2 of 1 to 0. And again, you have a similar problem with something that can't really be rewritten. It's just that's the closest you're going to get to like a simple representation of this value, and then minus 1. Ah. All right, and that's going to be the answer, guys. Um, I apologize that this was such a long video. It was not my intention, but at the end of the day, we do need to talk about this. And I apologize if that beginning part intimidated you or accidentally offended you. It's literally just like a genuine warning, which I don't know if my genuineness is like transferable in this video format. Sorry, I keep forgetting for the vertical watchers that you can't see me. But I'm right here. Let's see. Hello. I don't know if this will work. Hello. Oh, that's kind of weird. I shouldn't have done that. Anyway, not the point. Okay. But yeah. Um, take a breath, do a lap, and then go back to the group work. If you want, I'm gonna give you a warning right now for the washer and dryers. The washer and dryers. The washer. The washer and disc. That's the problems are 2 and 3 that are going to be those weird movement ones. So just keep that in mind. That I'm probably gonna literally take a break right now, but you can take a break as long as you want. Just make sure you watch it by the end of the day at least, so you stay on task. All right, so let me know if you guys have any questions, and I'll see you on the next one. Bye bye.